Okay, tonight we're lucky to have Neil Sinclair, who's an expert on making micro or nano photonics on chips. The work that he's talking about builds on things done by Marfa Lanchar and Misha Lukin at Harvard, making diamond chips with color centers in them that act as qubits, and then they managed over the period of about a dozen years of work to make a single crystal and nanophotonics that can really channel light around and begin to babble myself.
It's okay, Bob. Just leave it to me.
Qubits and the like. They realized that if you switch to a nonlinear optical material, lithium niobate, that kind of technology really opens a lot of wonderful things in nonlinear optics, which used to require like a whole table of optics. Now you can reduce it onto a chip. And so that's what Neil's going to tell us about.
Right, thanks, Bob. Yeah,
So, yeah, I mean, the chip thing is important, yeah, but I think the more important thing is the nano. We'll get to that, but like, so, yeah, I mean, we've already talked, so maybe for the YouTube audience, you can look me up, but the rest of the people here know. So we mentioned lithium niobate already a little bit, in that this is kind of like, in some ways, the standard material for mixing in this case the colors of light and also microwaves as well, right? This is nonlinear material. Photonics refers to light, so I focus a lot on light. Light being in this case around 200 or 300 terahertz. That's what I mean. It's kind of an infrared. Nano here refers to the fact that the interaction of the light of the crystal happens using devices that have hundreds of nanometers length scales. Okay, so that's where the nano comes in. We'll see that in a little bit. And so I said big data to quantum mechanics. Well, lithium niobate is known in prior to all the work I'm talking about here today. It's known since like the 60s for its use in like converting electrical signals to optical signals. Right, so this is where the big data comes from, in the sense that you have electrical signals generated by your computer or whatever, and you want to then convert those into optical signals, which can be carried very far. And optics light carries a lot of data, high bandwidth data. Right? So, maybe it's worth specifying this, but like if you have light here, 300 terahertz carrier for 300 terahertz frequency, right? This means that, if you have 100 gigabits or 100, I'll say hertz of data, right? Well, what this means in frequency space is you have a sideband that has a bandwidth of, 100 gigahertz either side, right? So this means you have 300 terahertz frequency carrier, so to speak, line, and then your data 300 gig or whatever, 100 gig on either side, right? This is allowed by light. You can think of trying to do this with microwaves. You can do this with microwaves strictly, you think of FM radio, right? Like 100 megahertz. You have 100 megahertz. You want to put 300 gig on 100 meg? You can't, because you're out of bandwidth, right? So this is the reason why light, this is why like people talk about fiber to home and wireless comm, laser comm, bandwidth, and that's enabled by light. And so it's an important challenge. What we talk about with lithium niobate is getting your electrical information onto light as carrier in these sidebands that I mentioned. Quantum mechanics, because lithium niobate is also heavily used in quantum optics experiments and industry now in quantum information science. And I'll talk a little bit about some of the quantum experiments that use lithium niobate. My training was in, I guess you could say, it was in atomic physics and also in quantum optics. And that as purely from a physics point of view. And I was drawn to this lithium niobate nano devices because I realized the power and also the versatility and the new physics that it could unlock. I'll talk a little bit about the sort of quantum physics, but I'll start with the data. I'll start with the sort of the more the bread and butter of lithium ion. Okay. This is a picture here of like sort of like an artist's rendition of what we want to make. We want a chip with a lithium niobate crystal, and then the lithium niobate is what underpins several different devices here. I just drew different ones. And we'll get into some of those later. But this is sort of the dream. You have a chip, you have novel devices, they're all lithium niobate based. Ironically, there was a student. So lithium niobate, its chemical formula is this LiNeO3. And ironically, Marco had a student, his name was Limbo. His name was Limbo Chow. It was like, I was just like, are you real? And he did so much work on lithium niobate, and he actually drew this picture. So I got a shout out for Limbo. But he's a really great guy. So he's over at Virginia Tech, working on lithium niobate phononics, which I won't speak about today, but we can discuss. This is a collage that I made, just to sort of highlight what our group is all about, just kind of an advertisement, you could say. So that's Marco, he's Marco Lanchar, so he's the professor that we work with. This is our website. This is a smattering of devices. Bob mentioned diamond, so if you do some in here, some diamond devices, as well as lithium niobate devices. And then this is us like having fun at Marco's house, and we do fun stuff too, but like this is like, if you're in our group, I still think that this other stuff is more fun than this. That's just me. This is kind of, I guess you could say, kind of a mantra or sort of our interests. I just threw it up here. We're fascinated by the phenomena resulting from interaction of light and matter in nanoscale structures. But matter here, we're focusing on lithium niobate. And we aim to engineer these effects to develop novel devices and systems. I may also say to see novel physics, new physical effects. And our efforts span a variety of materials, wavelengths, powers, both classical and quantum. Classical means somehow non-quantum, sort of like standard, strong. Like, it's a bit, okay, the definition of this is very rigid, but I won't go into that now. But classical usually refers to non-quantum. Let's just keep it at that. So let me start with, before we get into lithium niobate, let's think a little bit about one of its major, sorry, go ahead.
I have a question on the devices.
Yeah.
Like computations or devices for doing specific tasks.
Both.
So like
Oh.
this whole-
Yeah, so generally in a sort of, I apologize, that's jargon, and thank you for picking up on that. So when we refer to a device, we refer to something that we make at CNS in the basement that has some design. And we get a chip that has this design on it, we call that a device. And it does something, it has some input, it's output. Usually for us, it's like light and microwaves in and light out, or microwaves in. That's what we're referring to. Now, putting several devices together makes a device, right? That does, like you were saying, a computation. That could also be referred to as a device. But generally speaking, we're talking about the most sort of, you could say the more elementary components, which you call devices. Okay, so let's talk about, before we get into lithium niobate, let's talk about sort of one of the reasons why lithium niobate has been looked at prior to all this nano stuff. And it is in communication technology. Okay, so here's the motivation, like why are we doing this, right? Here's one of them. So this is kind of a cool, I stole all these from Marco, these slides too, so this is great. I thought it was pretty cool. Facebook connectivity map, I assume that, Instagram and Snapchat are probably similar. But this is, it just goes to show you that, how really strongly we're connected. this is kind of an interesting fact. In 2016, world internet traffic was 280 terabits per second, the equivalent to everyone in the world talking at once. Which is what, you know, I can't even send, you know, some of my family, let alone everybody. So, and this number is expected to continue to grow, right? So like we're data hungry and we want to be connected. And this is clear. You know, we've lived it, right? We're living this right now. Data centers, these are, you know, so-called the cloud, right? Or, you know, devices that are used to store and process information. These are believed to consume up to 10% of the electricity produced worldwide. So you can think of, you know, for a great example, Bitcoin mining, right? They like they go stake out, you know, they build like giant hydroelectric dams and just put giant server farms there, right? Why? Because they're so hungry for electricity. And much of the energy is wasted in heat. Right, so as we're familiar with that, right? These are CPUs. So a lot of this is lots of heat. So these are problems, right? So we use a lot of data, there's a lot of energy, and we expect more energy consumption. And in the future, we want higher bandwidth, right? So the coin 5G, you know, 5th generation millimeter wave. So we're talking about data bandwidths that are go beyond the current, let's say, gigahertz to hundreds of gigahertz. We're going here. There's no turning back. So the idea behind lithium niobate is that we use these lithium niobate, we use the so-called electro-optic properties of lithium niobate, which is really a fancy way of saying that microwaves can couple to light. Microwaves and light mix, like I mentioned before. And it's a very specific way that we'll talk about. But this sort of mixing of microwaves and light are what's key to enabling sort of addressing these challenges. Sometimes this is called a transducer because you're talking about transducing microwave data to optical data. Excuse me. Okay, so this is like a quickie slide on, you know, how this sort of wave mixing works that I kind of hand-wavy talked about earlier. So I mentioned that this is to understand this electro-optic effect. So I mentioned that lithium niobate is a so-called non-centrosymmetric material. So if you invert it, it looks different. So it does have mirror symmetry. This is the you know, fundamental. This is the fundamental lattice here. Lithium niobate, just so you know, it's grown like in a boule. So it's grown by like the Shklovsky method, let's say, which is you have like a seed and there's a bunch of gas and it's hot and there's pressure, and then the atoms will bond together in a way that, generally speaking, is lattice matched. Fun fact: most lithium niobate is really not stoichiometric. It's crappy. It's called congruent lithium niobate. And this is a 1-to-1, right? Lithium niobate to 1 niobate and 3 oxygen. Congruent lithium niobate is something like XY. It's actually hard to grow it in a pure way. Second fun fact: Julian Mundy is trying to grow stoichiometric lithium niobate.
Oh, really?
So that's here. So we're working with her on doing this. Nonetheless, it simply looks like this. Is the boule, looks like something like this big. And then there's ways of slicing this into wafers. That's what we use. And there's a way of like bonding the wafer. We'll get to that. Anyhow, we use the nonlinear optical property of the so-called second order nonlinearity of lithium niobate. So the light matter interaction is sometimes broken up like this. It's the Taylor expansion. Yep.
Is that, well, that's for polarization? Would the first term just be for a linear optic?
Yeah, this is linear, it's right here.
Yeah, okay.
Yeah, correct. So this is like glass. So you apply a field, you apply your laser pointer or whatever. There's a conversion, some conversion factor. it creates this polarization, that is, the charge is right in lithium iodide or whatever material moves. Those moving charges then produce light. That's why light, is, transmitted through materials. This Chi2 characterizes the strength of the second order interaction. So now if your E has two components, right? Frequency, you have two components. You have a field with frequency omega-1 and a field with frequency omega-2. You get squaring. So now you have, the cross terms, right? Right. So you have omega-1, cosine of omega-1 plus cosine of omega-2 times C, of course. And then you square it, and now you have four terms, you have cross terms, right? Those cross terms are what leads to the production of the sums of the differences that I mentioned earlier. This is called the curve. This is also exists, but this is orders of magnitude weaker. Okay. One way to sort of parameterize this mixing is you can think of in a linear material, this polarization I said was it's harmonic, right? Like you don't produce if we just have a linear material, you produce a polarization and hence a subsequent field at the same frequency. So in this case, the atoms can be perceived as a perfect parabola. That is a harmonic potential in a linear material. Right? You can think of linear material, apply your light, you move the charges, but they're moved like a simple harmonic oscillator. And then they produce light at the same frequency. Lithium iodide, that is a nonlinear material, the potential is nonlinear. Or not a problem. So it has some asymmetry. So when you apply your fields, let's say you apply omega-1, you're actually going to cause your charges to move back and forth, right? In your lithium iodide, but now it's not harmonic, but there's other frequencies. It's not straight simple harmonic, other frequencies. Those other frequencies that are there is what we tap into. Okay. Strong interaction, and then it's transparent, right? So, like I mentioned earlier, that's the nice thing. So let me, this is kind of very general, but the idea for the data center is the fact that this E will be composed of light, your carrier, and then you'll also have another component that is your microwave. So you have an optical component and a microwave component, two fields that you apply, and they mix. So that this is how you can get the data from the microwave onto the web. I'll show you. This mixing, a device now, thanks for great definition now. The device that does the mixing between microwave and optical fields is called a modulator. And the mixing itself, the mixing effect, is called electro-optic interaction. Right, but that electro-optic interaction, don't fool yourself. Okay. It's this. This could also be optical, but it's just a fancy word that people use. So the idea is that, for all of the big data applications and communications applications, we want to convert microwave signals, microwave data onto light. So this is sort of a rough schematic of how this would work. You have a electrical processor with your data, right, from your computers. Then you would couple this onto your modulator. This is where your lithium iodide would be. There would be a laser, and then that data would be carried by the laser frequency over fiber to in this case, a detector. So I'm talking about the detector here, but the detector really is just basically measuring a beat node, but we can get into that a bit later. But my focus here is, how do we actually get the microwave data onto the optical field. That is, how do we actually, how is it actually done specifically? How do we harness this nonlinear interaction so that the data can be put on the web? This is sort of the next question. But this is the general sort of idea of how datacom works, I guess you could say. I'm using fancy words, but I think you guys are ready for it. Okay. Mach center interferometer. Who's heard this before? Who hasn't heard this before? Okay, majority rules. Who's heard of an interferometer before? Okay, that sounds good. So the idea is that how do I say this? Okay, so an interferometer is a device which is based on resonance of waves, right? So you guys are familiar with like musical instruments. I think we can go back to high school on this one, right? Like, right, resonance, right? The strings are stretched, you hit the string, there's a standing wave, resonance, right? So an interferometer is a device that allows you to measure optical resonance. Okay, so, and you can change, usually this requires some endpoints. Here, right, it's the, I'm not, I don't play the piano, but there is some endpoints right on the string. Here, the endpoints are defined by beam splitters. So let me describe this. Light comes in. This is a so-called 50-50 beam splitter. Okay. What's a 50-50 beam splitter? Just means that 50% of the light intensity is transmitted and 50% is reflected. The window is like a 95-5 beam splitter because I can see myself a little bit, but the rest of the light goes out. I think it's something like that. But these are well made. These are 50-50. These are mirrors. This allows light to be combined again at another 50-50 beam splitter. What you have here is a resonance condition, and if you can change the phase of the wave, then you can create light that emits out one port or the other. That is, you have constructive interference at one port and destructive at the other, or vice versa. You know, the analogy is that you can set this phase to be some value so that all the light comes out of this port. In other words, you can set the phase so that you have this. Or you can set the phase that you have this. Nothing. But you hear it over there. So I'll show you the math in a sec. This is how it looks like on an optical table. So if you go down to some of the labs here, this is an optical table, has little holes in it. You put your optical elements here. This is a laser. Here's your beam splitters, your mirrors, and then these are little cards you can measure light intensity. Let's go through the math, how this works. Okay, so understanding how the interferometer works helps us understand how the data from the microwaves is imprinted onto the light. Okay. Go through the math in a sec. This is a quickie. How should I say? This is your sort of free space or your lab bench version. Now, how does it look on chip? Well, you replace your beam splitters with what we call 50-50 couplers. Okay, so these little, you can imagine that this light coming in, splitting in a beam splitter. Well, this is your beam splitter here. And what this coupler does is it allows a little bit of light to leak out of this path into the other. So if you design this right, you can make 50-50. And then they combine again, just like here. And the idea is that you put a capacitor around one of the arms. This is akin to this sort of a phase shifter here. And the idea is that you can apply a voltage. If you apply a voltage, that is, you apply an electric field. If you apply an electric field, you now have light and electric field mixing here. And you can do so in such a way that you can create the phase difference to be either 0 or pi. That is the phase difference of light traveling this arm with respect to the light traveling that arm. And you could get light coming out here, resonance, or not, or vice versa. I'll show you that in a second. One more slide. Okay. So light is a wave, right? There's a phase. The phase that light acquires in a medium with the length L and refractive index N. Refractive index is just parameterized by chi. I showed you before. And then remember I showed you the polarization. There was the chi terms that's related to them. Okay. So of course, like your wave travels, it picks up a phase. Now, the idea is that when you apply your voltage here, this electric field then will induce a slight change in the refractive index. Okay, this is another way of this wave mixing that I described to you. So that means now that you get an additional phase. So N is replaced by N plus delta N. And now you get an additional phase shift. So this means that if you apply the right voltage here, and let's say that voltage is pi, this voltage corresponds to a pi shift, then you can make this output port have all the lights, and you can then switch the output port such that the second one has all the light and this doesn't. So this is just simply wave addition. Yes.
This is all linear lines. These values are not linear. I think that's the Marcus warning. Very linear system.
Yes, so when you say linear, I mean like the fact that the data, the voltage is proportional to the shift.
Yeah.
Right? But the key point here is that that linear shift is enabled by the nonlinear crystal. So it's a bit tricky because you don't get this shift. This shift is enabled by microwaves or by electric field. I say microwaves, usually it's an microwave, this voltage. You don't get this shift unless you have that chi2, unless you have that wave mixing. This doesn't make this a 0. And then this is just be your chi1. So it's linear in the sense that your voltage is sort of transferred on, the signals are linearly transferred on the light, or the refractive index change is linear, but the core of the interaction is non optically. Right. So yeah, so here's the idea. You have your interferometer, you have your data. Look at either one of these. You have a bit, right? A bit could be 0 or 1, right? So let's say 0 is no voltage, and let's say 1 is some voltage. Let's call it high voltage. So when you apply your voltage, if it's 0, that means that the relative phase difference, let's say, is 0, and you have light that's output here. Now, if you have a bit 1, that's, I said that voltage corresponds to the pi voltage. Now, the relative phase difference is pi. Now, the light, there's no light up to this point, but there's light output here. So now you have the ability, through the Mach-Center interferometer, to turn on and off light based upon a voltage that goes on and off. This is how all datacom works. This is how all of our data communications work. It's based on interferometry. So that's it. That's it. It's interferometry. Now the key is, the challenge is though, how much voltage do you need? How fast do you change the voltage, right? How much light is lost? That's where the meat and potatoes are. That's where the money's made. That's where academics like us step up to the plate and try to solve these problems. And that's what we're aiming to do. So just let me talk about a little bit first so that you're aware of sort of the I would say how this was traditionally done. So this picture, yeah, Bob.
Line stuff up about 5 or 10 minutes.
Okay, sure.
Usually go for that.
Oh, okay, well,
But show some of the fancy gadgets.
I'll get there. I'll skip this. Let's skip this. Let's skip. Okay. So. The existing lithium niobate modulators, interferometers, are based upon, in this case, a type of cross-sectional structure like this. So you have your chip, a device. This is your typical modulator device. Light comes in, light comes out. These are fibers. You apply here a voltage through a port. This is about this long. Okay. Take home message that we need devices that were much smaller and much more efficient and require much less voltage. The legacy devices, this one, guide lights through their chip. So if you were to slice this in half and look at the cross section of what the chip looks like, you would find that the light is guided in this sort of region here in the lithium niobate. And this is defined by doping, changing the material slightly, doping in the fusion of titanium. So your light is confined here and confined here. This is a layer of protective glass, and then the voltage is applied here. So this is a ground. These are gold electrodes. This is the ground. These are the signals, and then you would apply a voltage difference here and here, and the electric field would enter the lithium niobate here. So that field is sensed by the optical mode that is in the lithium niobate, and then the strength of the field is what gives that phase shift. And that phase shift is what results in the data. Right?
How many volts do you have to apply?
This you're looking at here to get to something like 10 gigahertz. You know, you're looking at 10, 20 volts or something like that. But what we did, so like, what did we do? What are we all about? We shrunk effectively using the CNS downstairs. We etched lithium niobate. That is, we removed bits of lithium niobate so that the light, instead of sitting in this big spot, the light mode is sitting in a much smaller area here. This is on the order of micron, tens of micron width. This is on the order of, let's say, 600 nanometers width. So you drop down the cross section by an order of magnitude. What does that do? That focuses the light effectively. It interacts much more strongly, the light with lithium niobate. This improves the efficiency, the conversion. That is, you require much less voltage. So instead of requiring 10 or 20 volts, you now require 1 volt or less than a volt. So what this means is that in addition, you can also put the electrodes closer. You get an extra boost. So what this resulted in is our ability with just a few volts to be able to modulate signals that approach 100 gigahertz or more. It's not possible with existing lithium niobate, not possible with any modulator technology. And we did so in a way that was very low loss.
So where's the break? Is it that you can't make a lightweight system that's kicking out 20 volts at 100 gigahertz, or is it
A lot of power. You can. I mean, there's nothing.
Oh,
Microwave dielectric loss.
Yeah.
But I mean, I'm sure that if you know more than me on this topic, Bob, but there's a certain point when you try to design your microwave electrodes and you try to, not only that, but you try to then phase match. You need to also consider this at some point. There's phase and group velocity matching. This becomes extremely challenging when your light field is much lower.
Yeah, the device is just bigger than the wavelength.
Exactly. So this what I'm saying is quantified by this plot here, okay, so. This is the high voltage, the halfway voltage here. You know, you're looking at between 1 and 10 volts. And then this is the bandwidth, this is the frequency range over which. The microwave signals could be, right, so. Here, where really you want to be in this corner. You want to be able to have a very low voltage to reach high, and you want to be able to work at hundreds of gigahertz. You want to be able to push more data through with this very low voltage response. And our work, we were able to move to this curve here, and the existing sort of legacy lithium ion is down here. And there was earlier work on our sort of lithium ion mentioned this out. So this is kind of the, there's no quantum here, but this is kind of the take home for the data. I can jump to the quantum. Yep.
Why grounds on both sides? I really want the electric focus to be on one of the.
Yeah, it's a good question. So this is called so-called push-pull configuration. That is, when you have your interferometer, right, you split the light and it recombines. So when we apply our voltage, you upshift the phase in one arm and downshift the phase in the other. So you get doubly enhanced. Right, so you push the phase up and pull it down so that for a given voltage, you get double the shift. That's why we have two. Okay.
Let me fast forward. And we could talk, if you guys want to stick around later, I'm happy to talk more. So these are what the modulators look like. The interferometers. We did this on a wafer scale. We have three, there's a 6-inch wafer. We do 3 or 6. There's actually a company that was started by our group that does this. Let me get into, these are just a bunch of slides here. Quantum.
Yeah.
This happened, right? Last week. These guys, Espay, Clauser, and Zeilinger. I've met Espay and Zeilinger, but not Clauser. Zeilinger was here a couple of years ago, actually. I told him about lithium niobate, he really liked it. But these guys are you talked about why did physics, these are really inspirational. These guys did some inspirational work for me personally. A lot of their work was in entangled photons, pioneering quantum information science, right? And it turns out that lithium niobate is exactly the material, the workhorse material that these guys used in a lot of their research. What they did was they, in many cases, I mentioned entanglement, right? Quantum entanglement. Well, what it starts with is being able to create a, in their case, a pair of photons. So a photon being the most fundamental particle of light, an indivisible particle of light. These guys made entangled photons out of photon pairs. In many cases, lithium niobate. So I can talk a little bit about how photon pairs are made and entanglement, and how these guys used it. So I mentioned the wave mixing, right? This is another way to describe it. You can shine a strong laser, a pump laser lithium niobate, and because of the nonlinearity, it can produce 2 photons of different frequencies. Of course, they have to sum up to the pump for energy conservation, right? But this is sort of an energy level diagram of what that would look like. And in fact, when you shine a strong pump laser on a lithium niobate, what will happen is that under certain conditions, you'll produce a pair called the signal and the idler, and it will happen spontaneously. So due to quantum, you could say, if you've heard of spontaneous emission, if you've taken any quantum atomic classes. One way to think about this, that's, I don't know if it's controversial, but like, one way to think about this is, have anyone told you about vacuum fluctuations? Have you heard this before? Right, so vacuum fluctuations come from the fact that you have the uncertainty principle, of quantum mechanics. The uncertainty principle says that you neither have exactly one thing or another at the same time, sort of complementary variables. And the complementary variables I'm talking about now are energy and time. So it turns out that if you believe in the uncertainty principle, which I would say belief is a strong word, but you know, you can study that. It exists. You find that particles or energy particles can exist spontaneously for a short amount of time. These are what's the origin of so-called black vacuum fluctuations. That is, you have vacuum, you have nothing, and something can happen in vacuum. Something can happen out of nothing. You can create a lot of energy in a very short amount of time. And these vacuum fluctuations are one way to understand why this happens. Why is it that when you shine a laser onto lithium niobate, that spontaneously sometimes you will produce a pair of photons? What's causing this to happen? Vacuum fluctuations. Somehow there's a vacuum, a small amount of time where photons could spontaneously, or stimulate, I guess you could say, this event can happen where you produce a pair. Okay, and this is optimized. Like you can do this, you can make this pair. This can be all optimized. I won't describe that here, but you can increase the efficiency of this with lithium niobate. This is kind of the take-home slide. One of the take-home slides here. This dot. You pump lithium niobate. This is the setup. We produce a photon pair, and specifically one of the photons were at around 1.53 micron wavelength. No, this frequency is wavelength, and the other one was at around 1.59. So we fabricated the lithium niobate device, we engineered it, and we made here a photon pair. That was at one of the photons was at this wavelength, and the other was at this. Okay. So these photon pairs are what the Nobel people used. How did they use it? Maybe I'll leave it here as my last slide. With a photon pair, they can create entanglement. Okay, so quantum entanglement is described by a system that you cannot separate, or you cannot completely describe in separate quantities. You have to describe it as together. Okay. So this is an entangled state, quantum state, in quantum mechanical language. Here, this refers to a photon and another photon, that is a pair, arriving at an early time called, this is denoted by these ones here. Well, this is a pair arriving at an early time, and this corresponds to a pair arriving at an early time. And you can't split up this state up. This is entangled. There's a relative phase here. So how do you create this entangled state where you have a photon pair arriving either early or a photon pair arriving late? But you can use lithium niobate. That's what I'm trying to say. So, and it is a workhorse for this. So what people have done in the past, and what I've worked on, is that you can take a laser with a laser pulse. You can think of it as one photon, you can think of it as one photon. Now imagine that you send that photon into a Mach center interferometer, where there's a path length difference. So now you have a situation where your photon from your laser is arriving here either early or it's arriving late in superposition, because it's one photon. Right? It takes both paths to write a linear superposition. So now this photon is the photon which is sent to lithium niobate. This is the photon. And then what happens is spontaneously you can create two. The
photon arriving early and late? Well, if it arrived early, it goes into lithium niobate and it creates a pair. If it arrived late, it goes into lithium niobate and creates a pair, excuse me, early, late. So that's what results in this entangled state. Both photons early and both photons late. This type of entangled system or entangled state that is created by lithium niobate was a workhorse for several of those experiments that led to those guys getting a Nobel Prize. So I can't underestimate the fact that this material has played a huge role in the development of quantum physics. What we're working on, what we're able to show now is that we can, with our fabrication, we're actually approaching this idealized limit, whereby if you have one photon that you send into your chip, your device, with a very high probability, we can produce two. This is a one photon to pair. This interaction is extremely strong, extremely efficient. If we can do this, this could massively kickstart quantum computing and quantum networking and quantum information. All the stuff that people have been sort of like being promised for years and years. This is all enabled by the standard fabrication.
Why? It does that because your device is so small that the electric fields, if you like, are bigger in there than it would be in the larger.
That's correct. That's correct. So we've been able to get to something around 1% nonlinearity. So 1% of the time this can happen, so to speak. But there are known ways now for us to improve this. We can actually create resonators, create not just Mach center interferometers, but ring resonators, where we can trap the fields in time, not just in space. We talked about etching traps in space, we can trap them in time. And it's not, I don't want to say I can promise that, but there's a very clear path to the single photon nonlinearity. Another way to think about this is if you have a single photon nonlinearity, you have the ability to create a 2-qubit gate at room temperature, which could stimulate, the realization of truly practical quantum computers. But we're not there. I did some other work here I also worked part-time with Caltech, and we did some quantum teleportation using these entangled photons. And this is the stuff that quantum teleportation is also some of the stuff that those Nobel winners did. That was our lab. I'll just flip to the last slide. So this is a summary. Right, I said integrated lithium niobate photonics, chip scale modulators, efficient, fast. There's also some other stuff that's kicked over. But there's other functionalities I didn't talk about. We made lasers on chip integrated with lithium niobate. Excuse me, we're working on integrating diamond color centers, Bob mentioned, right? So one of the things one of the problems with diamond color centers is that they emit photons that are slightly different frequencies, and we can correct for that with lithium niobate. We can shift the frequencies very efficiently. We work with lithium niobate is also useful for quantum acoustics. I mentioned lithium niobate, because of its non-centrosymmetric properties, it's also piezoelectric. That is, when you apply an electric field, it produces a mechanical distortion of vibration. The quantum version of this is a single phonon. We are able to measure single phonons and control them. Why? Some of the world leading quantum computing efforts rely on controlling single phonons. This is because of their low noise properties and the sun. I mentioned the Bob earlier, optical computing. We're also working on using these modulators for neural networks. Because they're so energy efficient, we have the ability to perform high bandwidth optical computing with orders of magnitude less energy consumption.
I wish I could have got to those details for you guys. Another cool direction is synthetic photonics. We can simulate condensed matter systems with light. And this interaction between microwaves and light and light allows us to mimic some of the coupling terms in various condensed matter systems. And so we can study things like topological physics using these systems. We were able to make a frequency mirror. We made a mirror that acts and looks just like a mirror, based strictly on in the frequency domain, strictly by application of microwave fields, which is a weird thing, but there's a lot of advantages to it. And then quantum future is bright. So there's other, I mentioned single photon nonlinearity, large scale photonic quantum computing. Case in point, Psi Quantum, if you ever heard of them, they had over 100 million invested in their company. They're basing their approach on silicon, which is scalable and well known, but is slow. So eventually, when you start using your quantum computer, you want to make sure it's at a high clock rate. Silicon won't get you. We can do that. So the future is bright. I'll leave it there.
All right, thank you. Well, one last question.
We can go over slides later too. Yeah.
In the spontaneous, is it also possible to create straight quantum?
It is. But the key is, it is possible. But so the idea is that you want to be able to etch, or you want to create a device which suppresses the 3 or 4 or 5 or the n photon events, and you want to enhance only the ones that you're interested in. So the answer is yes. It's a weaker effect, but it is non-zero effect. So the name of the game is, when you're looking for studying these physical effects, the really cool thing about what we do is that you can control very precisely using fabrication techniques exactly what coupling you're looking for. I want to study that 1 to 2 coupling. Make the device, and we can study that. This is really, really exciting. And we can design it as you will.
So quantum will always be the same frequency.
No. So energy conservation is true. So let's say that this is the pump. And I showed the diagram of these two, right? Well, these two could have different energies. They could have, this could be a bit smaller, this is a bit bigger. They have to sum up to be equal to the pump, but they can be different. In fact, what can happen is that when they're spontaneously created, I drew 2, right? But there's nothing to really say in general that they have to have those frequencies. They could have a little bit less and a little bit more. So in reality, what happens is you produce a pair, but at a pair that has both a superposition of this frequency difference, this frequency difference, this frequency difference, create frequency entanglement. So frequency entanglement is actually created free. And most of the time you don't want it. You want time bending, you want that, you want to work with it. The frequency entanglement you get for free. You can use it, which we do,
But it doesn't work.
but it's more complicated, but it's certainly useful. I'm happy to talk about quantum mechanics all day. I wish I could have got more of a chance to get to that.
Well, okay, well, thanks again, and yes, yeah, he's a great selling, so thank you.
I wanted to keep running. I wanted to go away.
All right, well, punch the off button.
Yeah, I will.